Watch what happens when two independent processes attempt to transmit data through the exact same channel at the exact same millisecond. The signals crash and the information is destroyed. This failure state is known as a race condition. It occurs when multiple processes access and modify shared data simultaneously, causing their outputs to overlap, mix, and ultimately corrupt the final result. To prevent this, computer science isolates the vulnerable shared resource, whether that is a block of physical memory or an external device like a printer. This specific area of code where shared memory is accessed is called the critical section. Without protecting the critical section, the consequences escalate quickly. Two users sending a print command at once might receive a page with overlapping text. Two threads updating a bank balance simultaneously might overwrite each other, erasing a deposit entirely. Modern operating systems juggle thousands of concurrent tasks. They cannot rely on sheer timing or trust that processes will politely take turns. They require strict architectural control over who enters the critical section. The core issue of concurrency is not that multiple processes exist at once. The problem is their unregulated, simultaneous access to finite shared space. To enforce order and solve the critical section problem, operating systems rely on a highly specific mechanism, the semaphore. A semaphore is a dedicated synchronization variable explicitly designed to manage access to shared resources. You can see the logic mirrored in physical infrastructure. Think of a critical section like this single-lane bridge. It physically cannot accommodate two cars side by side. The semaphore acts as the traffic signal at the entrance, explicitly dictating who may enter and who must wait. Beneath that visual abstraction, a semaphore is remarkably simple. It is an integer value stored in memory. By modifying this number through very specific operations, the operating system dictates process execution. It operates as a digital checkpoint, translating a chaotic flood of concurrent requests into a strict, mathematically ordered queue. A semaphore's entire architecture relies on two fundamental operations that modify its integer value. These are typically called wait and signal. We can map the flow with this diagram showing two processes and a critical section controlled by semaphore S. For this to work, the wait and signal operations must adhere to a constraint called atomicity. This means they execute entirely or not at all, with zero possibility of interruption. Atomicity is non-negotiable. If a process could be interrupted halfway through executing the wait operation itself, the system would create a race condition inside the very tool meant to prevent them. Let's trace the execution. Process 1 requests access to the critical section by initiating wait. The semaphore instantly drops from 1 to 0, and process 1 enters the zone. Now process 2 arrives. It attempts to call wait, but because the variable s is already at 0, access is denied. Process 2 hits the barrier and is diverted into a queue. Process 2 has no choice but to remain completely idle in this queue for as long as the semaphore reads 0. When process 1 finishes its task, it exits the critical section and triggers the signal operation. The central variable immediately increments from 0 back to 1. With the value at 1, the system unblocks the queue. Process 2 is allowed to proceed, dropping the value back to 0 as it enters the zone. This precise numerical sequence guarantees mutual exclusion. Only one process can hold the access value at any given time. The entire mechanism holds together because of atomicity. Without indivisible operations, a locking mechanism is just as broken as the resource it attempts to protect. The model we just examined, where the variable is strictly limited to a 0 or a 1, is formally known as a binary semaphore. Binary semaphores are highly effective as mutual exclusion locks for a single asset. They work perfectly for a shared file or an isolated block of memory. But operating systems frequently handle pools of identical resources. Here we have a system with 5 identical printer nodes. To manage this without forcing processes into a single file line, we use a counting semaphore. Instead of toggling between 0 and 1, a counting semaphore's integer variable reflects the exact number of available resources in the pool. Here, s equals 5. As multiple processes arrive concurrently, they each trigger a wait operation. The counter rapidly ticks down to 0 as the system allocates all 5 printers simultaneously. When the value hits 0, the semaphore enters an exhaustion state. The resource pool is completely empty. If a sixth process attempts to request a printer during this state, the 0 value triggers a rejection, and the process is placed in a holding queue. The pool reopens the moment an active process finishes and triggers signal. The variable increments to 1, immediately allocating that open slot to the waiting sixth process. Software engineers apply this exact logic to manage database connection pools, limit concurrent network requests, and coordinate complex multi-threaded tasks. By utilizing the full range of integers, counting semaphores turn a single-file bottleneck into a high-capacity, multi-lane system that maximizes hardware throughput. In professional environments, you will frequently see binary semaphores confused with another mechanism called a mutex. It is a notorious pitfall to treat the two concepts as interchangeable. This split screen shows the architectural difference. On the left is a mutex, short for mutual exclusion. It is a strict locking mechanism. On the right is a semaphore. The defining characteristic of a mutex is ownership. The system tags the padlock with the process ID. As you can see, when an external process attempts to unlock it, it is rejected. Only the specific thread that locked the mutex has the authority to unlock it. Now look at the semaphore. It tracks no ownership whatsoever. One process can trigger the wait operation to decrement the counter, while a completely different process is allowed to trigger signal to increment it. This lack of ownership tracking is intentional. It gives semaphores the flexibility needed for producer-consumer problems, where one thread creates data and an entirely separate thread processes it. While you can configure a binary semaphore to mimic the behavior of a mutex, their foundational designs exist to solve distinct problems. A mutex protects a specific possession, ensuring only the owner can alter it. A semaphore acts purely as a signaling mechanism to regulate system-wide traffic. Because semaphores lack built-in ownership tracking, they are incredibly powerful, but entirely blind. Their success relies on flawless implementation by the programmer. If the wait and signal logic is poorly ordered, the system will hit this state, a deadlock. Process A is locked onto semaphore 1, but needs semaphore 2 to finish. Process B is locked onto semaphore 2, but needs semaphore 1. The math creates an infinite circular dependency. Both processes will wait on each other permanently, freezing the application until the operating system steps in to terminate them. Improper implementation also creates starvation, where a specific process is perpetually bypassed in the queue, or priority inversion, where a low-level task accidentally blocks a system-critical operation. Resolving these failures requires sifting through thousands of lines of concurrent execution states, making multi-threaded debugging notoriously complex for software engineers. The mathematical perfection of the wait and signal operations is ultimately only as reliable as the human code orchestrating them. At its core, a semaphore is simply a synchronization variable. It controls workflow through strict atomic wait and signal commands that cannot be interrupted. By ensuring isolated access to critical sections, semaphores eliminate the overlap of read and write commands, preventing race conditions from destroying shared data. Whether deployed as binary variables for single-file locks or as counting variables for massive resource pools, they provide the necessary scale to handle complex operations. They manage database access controls, coordinate threads in video games, and handle process requests inside every modern operating system. Behind the immense speed of concurrent computing, semaphores enforce the mathematical order required to keep our data intact.